I presume the speaker is Peter.
Yes.
Okay. Joint work with Dimi and Amin. And yeah, whereas the previous talks have been very much about, I guess, the underlying foundations of formulas in the first talk, and this one, the practical issues of actually, doing it all. This one is, well, it's about a debugger.
Yep. Okay. So, hello, I am Peter Chon, a second-year undergrad at Harvard College, and today I'll be presenting my work on Oxidize, which is a step debugger for static semantics. This was under Dr. Dimi Racordon of Northeastern University at the time, and Professor Amin of Harvard University. So what is Oxidize at a high level? It's a step debugger. And instead of allowing you to step through the dynamic semantics of a programming language, it allows you to step through the static semantics of a language that has ownership and aliasing. So it's basically a step debugger for a Rust-like language. And because Rust is the most famous representative of languages with ownership and aliasing, I'll be using Rust as like a notational abuse for Rust-like languages throughout the remainder of this talk. And Rust was our inspiration for starting this project that is Oxidize. So to understand what Oxidize is, it helps to understand what it is meant to be. So I'll motivate Oxidize, and I'll do this in two parts. So the first one will be why pedagogical tools for Rust are necessary, and the second is why Oxidize specifically. So the first, memory safety is hard. According to, I think, MITRE, 70% of security vulnerabilities are due to memory safety issues. And there are programming languages that offer memory safety through garbage collectors like Java, but memory safety and efficiency, that's the hard part. While thankfully Rust offers a way to marry memory safety and efficiency together, it does it through a novel type system that has been demonstrated to be hard to learn how to use. So I'm going to split people into two sets. First one would be programmers with systems backgrounds and those without this type of background. For those with a background in systems, it's been demonstrated that they have a hard time just like figuring out how to use a compiler that thinks about stuff that they typically think should be dynamic behavior. They find it hard to reason at a compile time. And as discussed in previous talks, for folks with this background, they're used to using a lot of patterns that Rust just completely disallows. And for programmers without this background, a lot of the borrow checking rules are just unmotivated. They're also unsure why we even have these, what they even are. Now, at the end of the day, like teaching these rules isn't that bad because there's only like a few rules about, piece of data can only have one owner, piece of data can only be mutably referenced by one thing, or maybe you'll have multiple immutable references. There's also a lifetime rule where it's like, reference cannot outlive the owner of the data it refers to. And these rules are easy to teach, but unfortunately knowing these rules doesn't suffice because we have a harder problem that's called incompleteness. And we can't solve incompleteness no matter how much we try to do. And it's just hard for everybody because even if we know these rules, there are cases when we're coding in Rust where we have perfectly valid memory safe code, but the Rust compiler just doesn't recognize that it is safe. An example of this would be with like splitting borrows. So now why Oxidize specifically? So let's look at the existing pedagogical tools that exist for Rust, and I'll contrast this with Oxidize. So the first one is Rustlings. Rustlings is a fantastic tutorial on how to learn Rust, but it teaches only the rules and doesn't teach how the borrow checker actually works. The Rust compiler error messages are famous for being fantastic, but they're too good at times, and it has been shown that programmers were tempted to just blindly copy the compiler hints and their suggested solutions. And because the temptation is that great, we just often end up doing so. So it's not going to teach them how to actually use the language very effectively. And occasionally, the Rust compiler hints are wrong. There's also the pedagogical tool that is RustViz. And what RustViz does, it allows teachers to manually annotate a snippet of Rust code. And it will generate visualizations on the memory events. For example, like when something is being moved to another location. And they specifically require manual annotation because what they want to do is they want to allow the teacher to highlight the relevant and most important memory events. And that is good, but I'll cover like in contrast, why Oxidize is like different from all of these. So first, we teach actual borrow checking. We don't teach the rules. It's like how the borrow checker actually works by simulating it through a static step-debugger. We try to force the user to think because we don't have like these fantastic error messages, and we show the user how everything is going, so they're kind of forced to confront the material. And there's no expert necessary, so you just write up some code, you run a step debugger, and that's it. There's no manual annotation necessary. So I'm going to do like a quick demonstration. This is not a live demo, but this is just like on the slides. So we have this snippet of code, and as we're stepping through it, we'll see that there's 3 types of context. So there's the type context, there's a memory map, and there's some borrow layout. So as we step through this code, we see that the contexts get updated. The borrow layout will check out, will just like do everything that borrow checker actually does. Memory map maps variable names to memory locations, which are natural numbers. And the type context, it stores the mutability of the variable and the type of the variable itself. Note that because it's a static semantics step debugger, it doesn't actually care about the values like 3 and 5. It just cares that these are ints. And eventually, we're going to get some borrow checking error. The issue here is that we can't assign to an address that's currently referred to. And we're able to show that, X is currently being mutably referenced by address 1, which is Y. And that is why we can't reassign the value of X, even though normally we can, because it's meant to be mutable. So now I'm going to get to the language presentation. So Oxidize is a step debugger, but it runs on a language that's also called Oxidize. And this language features stuff like immutable, mutable assignments, references, tuples, conditional expressions, ownership and aliasing, lexical scoping and lifetimes. I'll note that it doesn't feature some stuff in Rust that are quite important, for example, copyable types. The reason why copyable types aren't included, even though they're very important to understand how the borrow checker works, is that Oxidize is meant for beginners, and I remember when I was first learning Rust, I got quite confused because I would like write up snippets that only use primitives like integers, but integers are copyable, so that didn't teach me how move semantics actually worked. So I just disallow copyable types because they can just like learn, oh, this is copyable. Ownership rules don't really apply. That's simple enough. There's no type coercions because these would allow implicit dereferencing, reborrowing, reference downgrade coercions. These are quite important, but we're trying to keep this a bit like simplistic. We also don't allow traits. Traits are very important because they allow copyable, clonable, and other features, but we just like not looking at them. I'll also admit that we don't have functions yet, but that's like a to-do. Yeah. Okay, so now let's get to the grammar. So it's basically Rust with some OCaml conditional expressions. We also have unit as a keyword as an empty parentheses. And we have tuples using square brackets. So you have the standard integer type, the unit type, product types, which are types of tuples. And we have reference types, which store both the mutability and the reference type. And we also have borrow states. So we're going to first observe that a value at location L can be either moved to another location, be borrowed by reference at another location, or be dropped, which we can think about as being moved to an inaccessible location. So here are all the borrow states that I cooked up to like handle all of these 3 possible cases. So the reference, moved, and dropped are pretty self-explanatory. I'll note for the union, this is because of conditional expressions, because we have to unify what happens in both branches. So what the union does is states that, oh, all the states in this union are possible. So we're gonna have to handle all of them. So this is how like my rules kind of look like. So I'll note with this S, it's basically a borrow state, but it's kind of different. How they're different is explained in the paper. Anyway, so we have like our 3 contexts, gamma, which maps variable names to the mutability and type, mu, which maps variable names to the addresses they point to, eta, which maps memory addresses to their borrow states. And for example, if eta 0 equals ref b true 1, then the value of address 0 is mutably referenced by address 1. So as we saw on step 2 of demonstration 1, 0 is mutably referenced by address 1. So this would correspond with eta 0 equaling ref b true 1. So here are like some standard type rules. I'll also note that I created some helper functions like may drop and drop. What may drop does is checks that, oh, we can actually drop the value at a certain location, giving our context. What drop does is actually changes our borrow checking context. All right, so we're going to go through another demonstration that has more of the features of Oxidize now that we understand what all the context stuff that appeared on the screen actually mean. So we have our type context that stores the types, the memory map that stores the muse, and there's nothing relevant in the borrow checking layout. They're all nuns, nothing fancy going on, so we don't represent anything. So now that we're going to conditional expression, we're going to allow the user to select which branch they're going to go into. Let's assume that they said true. Well, then we're going to go to the true branch. There's not much going on, so it's just one step. Now let's go to the false branch, which is a bit more interesting in my opinion. So we see here that, let's see, so like, oh, wait, shoot, I'm so sorry. I forgot, okay. So one of the things with Oxidize is that tuples, though they're zero indexed like they are in Rust, the memory representation is a bit different, as you see here. Instead of being like C-style arrays, where the value of the pointer to an array is the same thing as the first elements, we offset it by 1. This was done purposefully so that users can know, oh, the tuple and the elements of the tuple, they're distinct notions. So borrowing one, like moving one or the other, they're quite different, as we'll see a bit later on in this example. So I went a bit too far. Okay, so we see here that 0 is partially immutably referenced. So the tuple A is partially immutably referenced, and that's because A.1 is immutably referenced by C. And whenever we're moving an entire tuple, what we do is we move all the elements corresponding to their new location. So 4 will be moved to, 0 will be moved to 4, 1, 5, 2, 6, 3, 7. And once we exit out of all the branches, we're going to have to unify them somehow because the true branch doesn't have anything special going on. We just use the false branch. But let's suppose that true branch actually had something interesting. What we're going to do is we're going to use our borrow state unions to be like, oh, all of these are possible. So the next statement's got to handle all of them. And we're going to, let's see. So like note, because of the static semantics, let's suppose that like it was like let b equals if false, then parentheses A.1. It would still say that 2 is moved to 5 because both are possible. And because we're trying to use A.1, even though it was moved to B, we get a borrow checking error as we desire because we're not allowed to use a value that's moved somewhere else. There's only one owner allowed. Now, here's our future work section. So I would like a better user interface, possibly using like a GUI, maybe something like Rust Analyzer where we have it in an IDE, and we allow the user to like use their cursor to select, oh, which location in the file they want to step at. We would like to simplify the formalism a little bit. The fact that we have like that weird S, that's not quite a borrow state, but it kind of is. I would like to simplify that in a nicer way. And I figured out some design choices. So the first one is tuple indexing. I've received comments that it is a bit weird how it's 0 indexed, but on the memory location wise, it's 1 indexed. I think it's okay, question mark, because I'm trying to like make sure that the user knows that these are distinct notions, but at the same time, it is confusing and it's supposed to be a pedagogical tool. So confusion is kind of bad. Also with stepping through branch unification. Right now, how unification works is, okay, we have the results from the true branch that we step through, the false branch that we step through, and the unification is just, okay, we have these, we're gonna, I don't like go through the unification and allow them to step through the unification process. I think stepping through would be great, but I'm unsure how to make that readable in a nice way. And there's also what to do with non-lexical lifetimes once functions are added. Currently, we only have lexical lifetimes, and non-lexical lifetimes, they offer some weird points, some awkward points on how to like step through stuff related to NLLs. For example, if a variable is no longer used, NLLs allow us to just like pretend that they don't exist anymore. But how we're going to show the user, oh, because it ain't going to be used anymore, we can just like get rid of it. I'm not sure how to do that quite well. Maybe we could do like some control flow graph visualization, but again, that means we're gonna have to find a better interface, and a lot of these stuff are kind of interconnected and stuff. But anyways, so this has been my work so far, and all the stuff I've been thinking about recently. Thank you for listening.
questions?
Thanks for talk. If I understand correctly, you are rather debugging like the type inference instead of executing a program like GDB does.
Yes.
So in that case, I'm wondering because when you type check a program, you may have, for example, a very complicated expression on the right-hand side of a let binding, for example, and maybe there is some type error that is related to some very, very deeply nested sub-expression. So in that case, can you also what is the best way to step into that? So from the user's point of view, how should I know that there is a type error? How should I use this debugger to step into it in a convenient way?
Oh, okay. So we do have type errors as well, but I haven't really thought about deeply nested types. Let's see.
Yeah, I mean some expression that is
Yeah.
deeply nested. Maybe there are
Okay.
some error, maybe not directly to time, but maybe some memory safety issues, whatever things that you can detect.
Okay. So in terms of deeply nested expressions, I think that's okay because if we look at how the syntax kind of works, it's basically Rust, but mixed with OCaml. One of the major things from OCaml is that everything's just an expression. So when we're stepping through an deeply nested expression, it just works as though it's just a chain of different expressions or statements. So I think stepping through that would be okay. for the
Yeah,
most part.
but my concern is that because in practice, if you really want to debug a really complicated expression, it's usually hard to detect which part of it is wrong. So
Okay.
yeah, but I think what you are proposing is more like a single stepping approach, right? You can just click, and then you see how the type checker works. But maybe the problem is that maybe after 90 steps, I realize, oh, there is something wrong. But this is usually not, yeah, this is a hard problem, but if you can address this to some extent, I think it will become more practical.
Okay.
Thanks.
Hey, I'm Will Creighton from Brown. I also implemented a static debugger for Rust, so come chat with me. And I wanted to ask concretely, is this interface, the ASCII representation of the type contexts with the currently executed instruction, is that as you envision it, the sort of final product? Or what is your dream interface for presenting this information to the user? Are there ways you think that you are hoping to simplify its presentation, or do you think this is as the end programmer should consume it?
Well, I'm partial to text user interfaces. At the end, I'm designing something maybe how Lean works. Because when you're proving something in Lean, there's a separate window that pops up and goes through the context in a much prettier fashion. I want something like that. Yeah. I don't know, but what the ideal interface would be is up in the airs, to be honest.
Okay,
Yeah.
thanks.
Hello, so I'm Jonas Fiala from ETH Zurich. And my question is, so you said you don't support functions, and I guess maybe you don't support loops as well? Or?
Oh, yeah, no.
No?
Sorry. Yeah.
So my question is, how hard do you think that would be to implement? Because this is where I imagine where a lot of the difficulty comes from and where
Yeah.
the necessity for lifetimes in Rust comes from, because you need some generalization at this point. So do you think it would be hard to add it to your language, or what is the idea there?
Well, I would assume that loops would be quite hard to add. Hence, they weren't added just yet. Are there any special cases I'd have to check for? I do think so. For example, let's see. Wait. Yeah, I mean, whether we're supposed to go through multiple passes in a loop or whether we're supposed to do a single pass, I'm still unsure about the details. I'm favoring just a single pass, doing oh, these are all the possible stuff that might happen using the borrow state union approach, but it's also less readable. So I don't know. Yeah.
Hi, so you mentioned that Oxidize is kind of like a language and debugger designed for learning. Do you hope that, is the intention for it to be something where it kind of helps you learn maybe like Rust-style ownership concepts, and eventually for like the user to maybe take off the training wheels and try other languages? Or do you see this as being used for like other, like continual use and for like professionals?
I don't think for professionals. I mean, I wouldn't use it myself besides like maybe to learn something about ownership principles. But yeah, so just for pedagogy purposes.
Okay,
Yeah.
cool.
Hi, I had a question that was sort of related to the last, so maybe actually your answer to the last kind of rules this out. But I was thinking it would be nice if you could do this like in response to error messages where you sort of flip the order that you do things, and like we ran into an error, now you can like step back. Have you thought about like doing things like that? Or even the other thing I was thinking of as far as errors is like identifying problematic branches. So you say like we could do this if we didn't need to also unify with this branch or something. How's that, like, are you interested in doing that approach?
So for the first part, it would be quite cool to add like a debugger of this sort into like the Rust compiler itself, but like I'm unsure how that process would look like. And for the second part, I have like thought about like when we're doing our branch stepping process, because like currently you have to select which branch you want to go down, and it would be much nicer to just like tell them, oh, is the false branch that is problematic or is the true branch that is problematic? But I'm unsure whether we'd be able to always detect which branch is incorrect. So yeah, I don't know, I haven't thought about that like too far.
So I just have a slight suggestion. Where you were saying about the tuples and having the addresses, have you considered using address ranges? Because then you could talk about the tuple being the range 0 to 2 or 3, I can't remember how long it was, and then the individuals could be the individual parts of that range. So then you could have it as a, not having to have a separate entry.
Oh, I haven't thought about that, but thank you for the idea, yeah.
That's all the questions. So,
Great.
yeah, thank
Thank you,
thank-
Ian.
Thank you.